Here we're going to talk about two groups of things. The first are what are known as the diatomic species, and the other is we're going to spend time talking about ions. So the diatomics are really there are 7 species that are elements, technically, that exist when they're by themselves as diatomic species, meaning these elements are so reactive that you will never find them sort of alone as atoms flying around in space, so to speak. And they are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These 7 species all exist as diatomic species. So if you find hydrogen out and amongst hydrogen gas, it exists as a diatomic H2 molecule. Nitrogen exists as an N2 molecule. This doesn't mean that nitrogen, when it's bonded with something else, like with oxygen or something, that restriction goes away. But if nitrogen's all by itself, it's diatomic nitrogen. If oxygen's by itself, it's diatomic oxygen. It's very rare that you're going to find a free oxygen atom. You can find oxygen that's not diatomic. You can find hydrogen that's not diatomic, but only when it's bonded to somebody else. So, for example, we talk about water, and water has oxygen, which is in it, but oxygen in the water molecule is not diatomic. The oxygen in the water molecule, it can be a 1, but if oxygen's by itself, it exists as an O2 molecule. It's a diatomic molecule. So all 7 of these all exist as diatomic. So fluorine and chlorine and bromine and iodine all exist as diatomics. And you need to know which ones exist as diatomics. There's a couple ways of remembering that. The first is that you can remember all the elements that end in the letters GEN or INE are diatomics. Another way of looking at it, a more creative way of looking at it, is to look on our periodic table. And if we look and see where our diatomics are, there's nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And if we actually draw a line going from one to the other, you see that it actually writes the number 7, so we can remember how many there are. And there are 1, 2, 3, 4, 5, 6 there. We don't talk about astatine because we don't really find it in nature at all. There's only 6 there, but we just have to sort of remember that the hydrogen is the other one. Last way of remembering it is the phrase, have no fear of ice-cold beer. So there's our hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. And what's interesting is if you remember this, you can also remember the physical states, that bromine is a liquid at room temperature and iodine is a solid at room temperature. Ice is a solid, beer is generally a liquid. Just easier ways of remembering all that. So in this section, now what we want to do is we want to talk about what are known as ions. Now ions are defined as any species where the number of protons is not equal to the number of electrons. So if the number of protons is equal to the number of electrons, we say that species is electrically neutral. We have no net charge, so all the positive charge that comes from the protons is canceled out by all of the electrons, and so we have no net electrical charge. As soon as we change that, though, and make the number of protons not equal to the number of electrons, we refer to that species as an ion. And we have 2 different ways of having ions. We can either have the number of protons be greater than the number of electrons, or vice versa. So if the number of protons is greater than the number of electrons, that means we're going to have a net positive charge, because not everything is canceling out. And if the ion is a net positive, we usually refer to that as a cation. And if the number of protons is less than the number of electrons, then it has a net negative charge, and we refer to that as an anion. And one way of remembering that is that if we look at the phrase anion are negative ions. Are negative ions. That's how you remember anion is the negative 1 and cation is the positive 1 by the word anion. So if we look on our periodic table, in the back of your problem set, you'll actually see it. You'll see this sort of stair step here. This is one way of sort of separating the periodic table into groups. And the reason why we're going to separate it into groups is because naming these ions and properties of these ions are going to be a function of where the element is on the periodic table. So this stair step sort of gives us the break point between what are known as the metals and the nonmetals. So the metals are to the left of the stair step, and the nonmetals are to the right of the stair step. These elements on this picture, as you can see, the elements that are near the stair step are sometimes referred to as metalloids, which is sort of a confusing concept, I know, and so I'm going to avoid it and just refer to, I'm going to try to simplify the world for you and just refer to you're either a metal or you're a non-metal. You're either to the left of the stair step, you're in the metal. If you're to the right of the stair step, you're a non-metal. Now, the metals and nonmetals also have a further sort of breakdown by these letters at the top, and those mean different things to different people, and there's different conventions, and we're not going to spend a whole lot of time about it. I just want to emphasize two of them, and those are these, what are referred to as A metals. So here are our groups. So there's 1A, 2A, and then technically aluminum, gallium, indium, and thallium are 3A metals, 4A metals, and the like. And these are known collectively down here as the B metals. So we have the A metals, and we have our B metals. And the reason why we would sort of want to talk about this is because this is going to help us in sort of predicting our oxidation states. Now, what do I mean by an oxidation state? So it's important for us to know when an element becomes an ion, what charge that ion actually is. We refer to that charge as common oxidation state. And so the general rules, and you need to be able to predict what the common oxidation state of each element of the periodic table is. So the general rules are that all the metals, so everybody to the left of the stair step, are positive ions. They can never form negative ions. That the group A and 1A and 2A metals, their common oxidation state is actually their group number, so +1 and +2. So sodium, lithium, and potassium are all going to be +1 when they are an ion, and calcium and everybody else in column 2 are going to be +2. Now all the other metals are variable. Everybody else to the left of the stair step. So if we go back one slide. So all these elements over here are always predictable. So these are always going to be +1. These are always going to be +2. And everybody else, all these other atoms, all these other metals are variable, meaning they can be more than one oxidation state, with 3 very clear exceptions, and those clear exceptions are right here. Silver, zinc, and aluminum. Silver, zinc, and aluminum. Silver is always +1, zinc is always +2, aluminum is always +3. How can you remember that? Group 1, Group 2, Group 3, and where they are. Those 3, you need to know that silver is always +1, zinc is always +2, and aluminum's always +3. So we go back to our other slide. So there's our 3 exceptions: silver +1, zinc +2, and aluminum +3. Now the nonmetals are usually less than 0, and they are predictable in their charge. Now the way that they're predictable, if we go back to our periodic table, again we're looking at these elements that are all to the right of our stair step, is by looking at this row right here. This is what is sometimes referred to as the noble gases. And the reason why they're referred to as noble gases is because they don't chemically react with anything. The reason they don't chemically react with anything is because they have very nice electronic configurations. Where the electrons are, they have a nice number of electrons. There's something special about having a noble gas sort of set of numbers. So they don't react with anything. Most chemistry is just pushing around of electrons. So let us consider for a moment fluorine. If fluorine was to form a negative ion, it's not too much of a stretch of imagination to assume that fluorine would only like to gain 1 electron, because if it gains 1 electron, then it would have 10 electrons. And it would have the same number of electrons around it as a neon atom. And neon is really cool. Everybody wants to be like neon because neon's a noble gas. It doesn't have to go and react with anybody to be stable. It's already stable. The reason why it's stable is because it has 10 electrons. So fluorine actually wants to gain 1 electron. And by the same token, chlorine, bromine, and iodine all want to gain 1 electron to become like a noble gas. The elements in group 6 like to have a negative charge, and they like to have a -2 charge, because if they gain 2 electrons, they also become like a noble gas. Will you find sulfur in a charge other than a -2? Yes. But when it's negative, its charge is -2. When chlorine's charge is negative, it's -1. Chlorine and sulfur can have positive charges, but when there's negative, it's predictable. And we mentioned earlier that all the elements in group 1A like to be a +1 charge, and now you understand why. That if sodium, which has 11 protons as a neutral element, if it loses 1 electron, it goes down to 10 and has the same number of electrons as a neon, so it's stable. That's why these elements are always, when they form ions, these are always +1, and these in group 2A are always +2. You'll never find these as a +1 ion, nor as a +3 ion, because if they lose 2 electrons, so there's calcium, if it loses 2 electrons, it gets 18, it has the same number of electrons as a noble gas, which is why it forms that +2 charge. And of course, then you have all these variable ones sort of in the middle. The reason why they can vary and you can have more than one oxidation state as stable is because, well, partly because they're so far away from the noble gas configuration. So they actually, for example, you're not going to have ruthenium here with 44 electrons. It's not going to become a +8, such that it could be like krypton. Losing 8 electrons for ruthenium, that's just too difficult. It actually can't get to a noble gas configuration. So the last thing we want to mention here is the naming of, and how we name these anions, or cations and anions. So, because it's going to become important when we start naming molecules. So the way we name cations is, no joke, simply the name of the element followed by the word ion. Sodium as a +1 ion is simply referred to as a sodium ion. We actually don't indicate the +1 because sodium is always +1. It's in group 1A. If I say sodium ion, the implication is I know it's +1 because it can only form a +1 ion. For the same reason that I refer to calcium 2 as just, I don't have to refer to it as a calcium +2 ion, I just refer to it as a calcium ion because calcium can only be +2 because it's in group 2. But iron, it's one of those B metals, those metals in the B area, and so it can have more than one oxidation state. It can have more than one charge. And so I have to be very clear as to which flavor of iron I'm talking about. So I can't just say simply iron, ion. I actually have to say iron 3. Now notice the iron is a +3 charge, and the way we designate that is by putting a Roman numeral in parentheses behind the word iron. That's how we indicate it. Manganese 7 is written, so here's my manganese atom. It is a +7. And so it is an ion, it's a positive ion, it's a cation. And so the rule is we just say the name of the element followed by the charge, ion. So the way we read this is manganese 7 ion, not manganese VII. This is just Roman numeral, and that's just the convention. Anions, however, you actually change the ending. So instead of referring to them as, so fluorine as a -1 ion is not referred to as a fluorine ion because it's an anion, and so we change the ending and turn it into "ide." So again, fluoride is it's a -1 ion. Fluorine is predictably -1 when it's a negative ion, so it's simply referred to as a fluoride ion. Oxygen as a -2 ion. Again, it's predictable, so we just refer to it as oxide. And sulfur right below it, it is also predictable because it's 2 rows away from a noble gas, and so sulfur as a -2 ion is simply referred to as sulfide. And as I mentioned before, the nonmetals can be positive in charge. And so in this case, this would be a sulfur ion as a +6. So cations are just the name of the element followed by the word ion, and anions all end in IDE.